for the nuclear force to act on it so that something could bind together. So this doesn't look right because the sun is not that hot. Here comes the idea of tunneling. We need tunneling to achieve fusion. So the picture now becomes the proton does not have that much energy, not that high, okay, but much lower. So how could a proton tunnel into the vicinity of another proton so as nuclear force could grab and combine them into a bigger nucleus? Of course, under our theme, the mechanism is due to tunneling, okay? A good reason is that the temperature of the sun, even if you go to the center of the sun, is not that hot. The surface is even cooler, right? And this is one important chart in nuclear physics. There is a second one about the stable nuclei, the number of neutron, number of proton, okay? You see that. So this is another one. The y-axis is the binding energy per nucleon. Per nucleon is important here, okay? And then this is various different nuclei, the mass number. We are considering things up here, okay? So this is deuterium, and then look at helium, boom, goes up here, okay? So helium per nucleon has about 7 MeV per nucleon binding energy, okay? And that is why fusion could release energy. Two hydrogen or deuterium hydrogen comes together, it is climbing up the curve. This is more stable, by that higher, by that I mean higher binding energy per nucleon, okay? And then if you go through this curve further, there's a peak somewhere here. That is the most stable nuclei, iron, nickel, those kind of things. And then it becomes a mystery about how this can be formed, right? We want to gain more energy, so we always want to climb up this curve, but then how come we have that? That's the story about supernova. We are not doing it here. We are just looking at climbing up from this beginning part of the curve. And that is why fusion could release energy, a lot more than burning coal. So the energy from the sun comes from this climbing up on this beginning part of the binding energy per nucleon curve. There are two sets of possible cycles proposed by a physicist for this mechanism. One is called PP cycle, proton-proton cycle. Here are the processes. There are several ones, okay? But for cultural purpose, I think it is important to at least know a little bit about them. So the first step is the most difficult step. I mean, the most difficult to occur step. Two protons comes together, form a deuterium. It is a weak interaction process. It means there's some neutrino involved. So to balance the charge, you have a positron coming out, and then positron has a cousin called neutrino. This is the solar neutrino. So that is a big part of another story. And that is the thing that, you know, thousands of people try to measure the neutrino coming from the sun. Once you have this, life is easier to move on. You have deuterium proton, then you have a helium-3. Some light comes out, gamma ray, and this gamma ray, that there is some energy coming out to be shared by these two products. And then when you have helium-3, two of them then come together, form a helium-4, that is the end product that we want, and then some proton comes out and you get a lot more energy out, okay? So now if we add up these three processes, the net is 4 protons come together to become a new helium nuclei. You have some positron, some solar neutrino comes out, and a lot of energy, okay? So we rely on this energy for our life, supporting our life. And some nice thing about weak interaction, so we are enjoying our life due to weak interaction. Now, this #1 process is a beta decay process, which does not occur very readily, very slow. That's why our sun is burning slowly, just enough to keep us warm, but don't heat us to death, right? So that's nice. And the sun is burning very slowly because this process does not occur readily. And you can estimate how many years can it keep on burning, okay? And there is one mystery about the solar neutrino. So we know this process, therefore people set up experiments on Earth using some underground water tank and so on, and try to measure this neutrino for many, many years. I think neutrino was proposed by Pauli in the early 1930s, because in beta decay, the electron comes out. When you measure the electron energy, there is a distribution, okay? So by a distribution, it means sometimes this value, sometimes that value, but the decay should have a definite energy giving out. So a mysterious particle must take up that missing energy. And Pauli said, this is a tiny neutral particles. So in Italian, it is neutrino, okay? So from that point on, also this solar energy mechanism was proposed in around 1930 something, when nuclear physics became very popular at that time. Then people start to set up experiments to measure this solar neutrino. After many years of work, in the mid-1990s, over many years of data, scientists realized they counted only maybe 60% of the expected number. So there is a large number of solar neutrino not accounted for. That is called the solar neutrino problem in the 1990s. At the same time, theory side also developed, and there is the idea of neutrino oscillation. So the solar neutrino coming out from the sun are of the electron type. That's why I have a subscript E down there. From theory, it was realized that as the neutrino travels, that's a long distance from the sun to the Earth, there is a probability that the electron neutrino will so-called switch the flavor to some muon neutrino or even to tau neutrino. Thereby, as they reach the Earth, part of them, when you intend only to measure electron type neutrino, you do not count that many. All right. Then comes several experiments, some of them in Japan, very big tank of pure water, so on. One of them is in Taiwan. Okay, Professor Zhu Meizhong is one of the founder from the first day till the end, okay, of the experiment. So from nothing, well, but in Shenzhen, the best thing is that those nuclear reactors are the most powerful one on Earth, basically. I mean, the megawatt that they produce every day. Thereby, there's a lot of free of charge neutrino coming out. Okay, you work on it, you don't work on it, they come out. So they dig tunnels into the hill around Taiwan, and then they put 3 big tanks of pure water there with a very sensitive detector. At the end, they achieve measurement of one important fundamental parameter that governs the probability of flavor oscillation. And that is regarded by physicists in the world to be the very first international level big experiment result coming out from China. Okay, and that is the solar neutrino problem. Okay, so let's get back to business about tunneling. So that is, fusion is how we get the energy from the sun, okay, and support us. Then there's the idea about, can we get fusion energy on Earth? Now that has been an idea for at least 70 years, I think. So to design something on Earth so that we have so-called controlled fusion. So what is controlled fusion, or what is uncontrolled fusion? Uncontrolled fusion has been achieved after the Second World War, okay? The hydrogen bomb, so-called. You just do something and let it bomb, okay? Don't control it, that's done, okay? But now we want to play it safe. Can we have controlled fusion as the energy of the future? It's regarded as one way. I think increasingly more people are thinking about this line, especially when climate change becomes a very urgent issue. It is at least regarded as very clean. There's nothing harmful that will be produced. So there are many projects, international projects on Earth now going on. A particular eye-catching one is called ITER. It is called ignition project, something like that. 點火啊，點火. Okay, so so this is the project is ongoing. I think it's being built now in somewhere in France. Many countries joined the effort, and it is projected to be trying the experiment in a few years' time, and then maybe 15 years later, you do have proof that this idea worked. I give you a link here. You can go to that link and then look at the details. But 2 months ago, there is some so-called breakthrough. This is another international project called JET, Joint European Torus. A torus is the thing that something like this, okay? Inside here, okay? You see something like a donut shape inside a donut, a tunnel inside a donut. That is the torus, because we want very high temperature, 10 to the 8 Kelvin, 10 to the 9 Kelvin, to push proton together to form helium, to fuse together. Okay, so there's no container on Earth that could support something that hot. So this plasma, the charge things, does not touch the walls. They are confined by very complicated magnetic and electric fields. And that is inside the torus. Okay, so 2 months ago, there is a smaller and similar project, and they are related to ITER. This is the Oxford site, JET. They announced, make a very big announcement, press conference, that they got some energy out and demonstrated the potential of fusion energy. What they got is 5 seconds, 5 seconds only, 59 megajoule. So how much is that? Okay, let me tell you. I think it is about, this bottle of water, maybe about 30 bottles of them, and heat them up, boil them. That's about that number. Okay, so not a lot. You can easily do it. Okay, but at least by fusion, they claim that they have achieved this. Okay, let me see.
What's it like to learn math? I'm really
sorry, so I cannot share the screen here. I'm trying. Right there. Never mind. You click on the link and then you will see something very fancy. Okay, so for this press, some question, how many years away? Well, I think it really depends on how urgent the issue of energy crisis will be. Okay, because in the past we have historical similar situation in the history. So in the 1970s, there's an energy crisis, and then because of the Iran war, and then at that time, when many governments put their money into energy research, then suddenly the progress become much quicker. Okay, then when the oil prices drops to a very comfortable level, just like 2 years, 3 years ago, $40 US per barrel, all the governments say, I just use that. Okay, so it really is not entirely a scientific barrier to go through. It has to do with the investment of from the international community. Okay, but I think now it's a lot more serious. So I think in your lifetime you will see that. Okay, maybe not in mine. So where am I? I cannot move my page.
But also general. We are here. The slide itself is based on
Oh, sorry, somehow we hear the we hear the press conference. So I'm
Professor Fusion, which is the world's largest fusion consortium. We are 30 national research institutes in the EU.
Sorry, I don't know how to stop it. I don't know which screen is this.
We can use fusion to provide clean, safe, and abundant energy for future generations. On the screen, you see the logos of the 30 national institutes, but behind them, there are 150 universities, companies, and organizations.
Okay,
and
so
about 4,000.
So I encourage you to at least take a look of this press conference, and they have a very fancy 5-second movie showing the growth inside the torus. So how can I stop this? And then I can go back to here. It's not working. Sorry, I have a few pages I want to go, but I need to reopen my file. Okay. So there's a question actually, how do they extract the energy from fusion? The plasma is not touching anything. I don't know the answer, but again, I give you the 2 links to the 2 big projects. You may want to look into that. Okay, Mr. Tai? Okay. So let me continue. I think your generation should be aware of this, okay? So you can click here or you can click there, okay? Then you get a lot more information. Besides this PP cycle, I would like to mention another possible cycle for fusion. So when a star keep on burning, after it has some helium, then helium could also fuse to become bigger and bigger nuclei. So when a star have been burning for a while, it may have some carbon, nitrogen, and oxygen inside. If this is the case, there is another possibility called CNO cycle. There are many more steps here. So you have carbon with a proton forming a nitrogen, and then weak interaction forming carbon-13, and so on. You have nitrogen-14 climbing up to be bigger, and nitrogen-14, oxygen-15, and a weak interaction again. And then at the end, you get some helium, okay? So now if you add up all these processes, the net thing is something like this. And this is proposed by a very famous quantum physicist, Hans Bethe. Basically, Hans Bethe was around in Europe with Pauli, with Heisenberg, with Max Born at the beginning of the quantum mechanics. So he proposed this and he got the Nobel Prize in 1967. And for those who want to have a better historical perspective of the development of quantum physics, you can Google American Physical Society interviewed Hans Bethe. Well, he passed away, but before his death, they interviewed him and had cut it into 152 minutes short interview clips from the early days when he was very young, a friend of Heisenberg, all the way through. He was the head of the theoretical section in the Manhattan Project, making the nuclear bomb in Los Alamos, and then how he first encountered Richard Feynman in the Manhattan Project. Feynman had not got his PhD degree yet at that time, and then later on, how he got into more and more quantum and nuclear physics research at Cornell. So that is a very nice record by someone who are involved from the beginning in the development of quantum theory. His Nobel Prize was obtained for his contribution to a theory of nuclear reactions, especially for his discovery concerning energy production in stars. And this is this particular cycle that he won the Nobel Prize. Our sun relied more on this cycle than the CNO cycle. So I would like to show you this recent paper, 2020 paper in Nature. So as a big collaboration again. So they try to measure the neutrino coming from this particular CNO fusion cycle. So they could estimate how many percentage come from the PP cycle, what is the percentage that come from the CNO fusion cycle in the sun, okay? So it is an Italian underground laboratory measuring solar neutrino again, okay? And then they can pin it down so that they could also inform astrophysicists how much carbon, nitrogen, oxygen are there in the sun, and what is the rate of changing of these elements in the sun. So in conclusion, they found that CNO fusion of the sun is to be of the order of 1%, and the rest is the PP cycle. Okay, so you see, it is not a 100% known knowledge. It's still a topic of frontier research. I know you know that in recent years somehow the biggest thing, and particle physics, the smallest things, come together to become astroparticle physics. Professor Kenny in the department is one of those younger ones who now doing research in this astroparticle physics. So this is astroparticle physics. The event is weak interaction, and then it has to do with astronomy. I already mentioned this earlier. This remaining 3 pages are just some remark on tunneling. So I mentioned this resonance tunneling, double barrier. You can easily work it out. You will get 100% tunneling at selected, very definite energy below the barrier. Okay. The physical reason is that when you see a structure like this, forget about the two sides. It looks like a finite well. A finite well will have some bound states here, right? So this bound state will remain. There is some signature of this bound state even in this structure. This is no longer a flat barrier, they come down, okay? But nonetheless, there is this structure here indicating some energy is playing a special role. So it's like electron coming in here, it has a step in the middle for it to tunnel through. So when it has a step, it is easier than just tunnel through the two barriers. That's why you have a sharp peak at some selected energy. Once you have this very sharp structure, people are thinking about switching devices. Weak, strong, and then you have 0, 1, things like that. So that will be an interesting application. So this experiment was done in Japan, NTT lab. NTT, I call it Thomson telephone company. Another one I would like to introduce to you is something called quantum cascade laser, a very clever thing. So you design the structure, when you apply a potential, the profile is like this, okay? So each well has two states in it, but they are aligned. So they tilted, that is applying a potential. You tilted it in a way that, so when an electron comes in here, it drops down, so a light comes out, it will tunnel into this place. It is in the upper level, it comes down again, another light comes out, and so on, okay? So it's a very clever thing. It is called quantum cascade laser. The one who invented it is Capasso. He invented it in Bell Lab. Invention is so important that Harvard attracted him to be on its faculty. If you are going to bet on a Nobel Prize, this may be a good bet, okay? So there are other applications more closer to your daily life. In flash memory, now you can turn on a device very quickly. Basically, it is also a tunneling dependent device. So all this kind of things called MOSFET and so on, when the size get too small, tunneling will get in. So modern day engineers, I think they ought to learn some quantum mechanics. So let's end our discussion on this part. I give you several references, some very practical thing written for electrical engineers, and then some related to nuclear physics, because we talk a little bit about nuclear physics. On the pure theory side, the tunneling thing, of course, is discussed in Griffin's Introduction to Quantum Mechanics. So that's the end of the course. So as I said, this tunneling part is optional. It is excluded from the final exam. All the things from the beginning to the end of the molecular spectrum discussion will be included in the final exam, except those explicitly marked optional, okay? So for example, in some sample question in your homework problem, a calculation is too long, only appropriate for problem set, then that will be excluded, all right? You look for those optional marks, okay? Other than that, everything will be included. It will be comprehensive. I'm still thinking about the whole procedure, but I imagine it will be pretty close to the procedure in the midterm exam. I have to arrange more TAs in, so I will call some help, but I will send out some announcement in due course, all right? So that's the end of our course. Let me summarize the whole thing very simply. We introduced a few approximation methods. There's not much about them, but when you are equipped with a few not so complicated approximation method, including variational method, perturbation theory, that include time-independent, non-degenerate and degenerate, and time-dependent perturbation theory, we can understand the minute details in hydrogen atom and other atoms like spin orbit interactions, Zeeman effect, the enormous Zeeman effect, things like that. And we can also understand the bigger atoms by the Hartree self-consistent idea, things like that. And also we can understand why two atoms can bind to form a molecules. And we can also understand how the nuclei motion affects the molecular states. And also we can understand atomic spectrum, molecular spectrum, and we don't have time to go through it. Actually, we can understand a lot of nuclear structure from this Hartree self-consistent idea, and spin orbit splitting is also a part of understanding nuclear structure. Okay, we also talk about how tunneling threads through many fascinating phenomena. Okay, so with that, we end the course here. I don't want to see you again in this course next year, of course, and then good luck in all the other business in your future. Probably I will not see you next year. You will promote to year 4. Okay, so I will end the course here. I will stay around for some questions. Bye-bye.